And hello, Calculus 2 students. This is the last section for this course, and it is basically a review of conics from your college algebra course. Now, I've included a document in there in your course that is called Conics Made Easy. It is the document that I give to my college algebra courses. I made it as like a guide. So if you've forgotten how to do your conics, you might want to review that document. It covers all of the different types of parabolas, the two parabolas opening up and down, and then the parabolas opening left and right. It even covers the directrix and goes over the vertex of the parabola. Here is a parabola opening to the right. It has the form y squared equals px, and if you'll notice, your directrix is y equals negative p, and it tells you how it's symmetric. This one, of course, is symmetric about the x. In our first examples, we're to find the focus and the directrix. So let's look at our equation and note that it is of this form here. So that lets me know that 4p is going to equal the minus 12. So I need to figure out what p is. P then equals negative 3. If I know that p is equal to negative 3, the focus then is, we have this one here, the focus at P0, so that would be the focus is at negative 3, 0. And then we need to find the directrix. The directrix would then be at, let's see where they have it in here, x is equal to negative p. So x equals a negative negative 3, which would then be 3. Next we're to sketch the graph. So let's get some grids. And here we have our graph where our focus is at negative 3 and the directrix is at x equal to 3. Example 2, we're going to do the same thing again. We're going to find, well, no we're not, we're going to find the equation of the parabola with the vertex 0, 0 that opens downward and passes through that point. So I know that it opens downward, so it must be of the form x squared equals 4py. Alright, so I know that it is of this form. Then I know that it satisfies this point, so let's just go ahead and plug in that 2 squared equals 4p times negative 3. So I have 4 equals negative 12p. That lets me know that p is equal to negative 1/3. And if that's my equation, then I can just say that x squared equals a negative 4/3 y. And is that all I need to do? Find the equation. That's it. Now we are finding the focus point, and in finding that focus point, it has a very useful application, and that is for our satellites and our transmitters and reflectors, our receivers of different signals. So you'll need that focus point in order to know where these signals will bounce towards or away from. Our example 3, we're reviewing our ellipses. If you'll remember, you will know your major axis by whichever variable has the largest number under it. This x is, you'll take the square root of your denominators here as long as this equals 1. And so x is what I call wamperjawed by a 3. So on either side, the vertice there, for this one would then just be your plus minus 3, 0. for the x-axis, and you will notice that your y is wamperjawed by a 2 here. A is just your largest number, so A in this case is 3, and B is then 2. So note that I have this case here for this first one, and that means I've got to find C so that I can get the focus. Oh, they want the, so let's go ahead and get the focus. So that is 3 squared is equal to 2 squared plus C squared. Computing this, you'll get C is equal to plus minus square root of 5. This means that my focus points are positive, negative, square root of 5, comma, 0. And then we've got to get the length of our major and minor axes. Well, if x has a radius there of 3, then one on either side. The major axis has a length of 6. The minor axis is 2 wamperjawed on either side on the y, so the minor has a length of 4. I think I answered all the questions, and there's the graph of it. Alright, so let's see, we have in question 4, its focus is on the y-axis, so if its focus is on the y-axis, and it has a length of 8, so that's 1, 2, 3, 4 right there, 2, 3, 4 right there. Minor has a length of 2, so that goes 1, 2, 1, 2, there, and there. And that would mean the y is the one that has the A, so that is a length of 8, so that would be a 4, so this would be the number 16 plus x squared over, and this is a 2, so that's going to be a 4 here equals 1, since it's centered at the origin. Find the equation of the, oh, that's all I had to do. Oh, I've got to graph it. Okay, get that graph, and here's our graph, what we drew before. They didn't ask us to find the focus, but we could have found the focus just by doing a squared equals b squared plus c squared. Not a big deal there. Alright, we're looking at hyperbolas now. These are hyperbolae on the x-axis, and these are hyperbolas that are on the y-axis. That would look like this. We happen to have one that is along the x-axis because the vertices are on the x-axis, and the focus are as well. So I know what my A and my C are. A in this case is then 4, and C in this case is 6. So in order to find the equation of that hyperbola, well, I know that it's going to be some x squared over a number minus y squared over a number equals 1. I know what the x is over. He's over 16 because of this 4, but I need to get my b value, and I know that b squared is equal to 36 minus 16, just following this equation here, and that would give me that b is equal to a 2 square root of 5, because that would be 20. Take the square root, pull out the 4, and that would give me, if I square this, it would be 4 times 5, so this would be a 20 under here. And that's all for the hyperbolas. Theorem 11.3 is our relationships for our eccentricity and directrix, and they are given here. And once again, just more review from college algebra. This yields a nice summary for my ellipses and hyperbolas. You can also look at the Conics Made Easy document, where I go over an example of each individual case and finding those directrix and eccentricity and the major minor axes and how to graph each of these conic shapes. Alright, we have all of the information that we need here. I can see that since the focus points are along this y-axis, we know that we have, y squared over a squared plus x squared over b squared equals 1. So far I know that c is 4. I can use these equations here to get my a and then my directrix and then get my b. So they tell me that e is 1/2, so I know that c equals a times e, so I have 4 equals a times 1/2. That gives me that a is 8. So far I've got y squared over 64 plus x squared over something equals 1. I know that for an ellipse I have this. So b squared equals a squared, which is 64, minus c squared, which is 16. So this will give me for my b 4 square roots of 3. Squaring this and putting this under 8 would be 16 times the 9. So hold on one second. Sorry, I mean 16 times 3. What is wrong with that? That is 48. Alright, so I have my equation. I need to find the directrix. They want me to find that too, and that's a over e, so that's a over 1/2. So the directrix then is going to be 16. So the directrix lines are both equal plus minus 16, and I think I need to say the vertices. The vertices are at 0, plus minus 8 for the major, and then for the minor it's plus minus 4 square roots of 3, 0 for the minor. And graphing, that would be our graph right there. Alright, looks stunning. Alright, in this last set of examples, what we're going to do is basically do our new material. We need to get our equation in a general format. I notice that I'm going to have one of these two. So I need to have a 1 plus. I'm going to divide top and bottom by 2, so that'll be 4 over 1 plus 3/2 cosine theta. Alright, that means that my e is then equal to 3/2. Since my e is 3/2, that is greater than 1, I know that I have a hyperbola. Okay, so I've got a hyperbola. I know that e times d then equals 4, and if e is 3/2, that tells me that d is then 8/3. So if my directrix is 8/3, then what we will need to do is we're going to let our theta equal 0, and we're going to let our theta equal pi, and we're going to plug that in and see what we get. When we do that, if you plug a 0 in and do your computation, you will get that the polar coordinates for the vertices in polar are then 8/5, 0, and -8 pi. So in Cartesian coordinate system, this is, so I'm going to write Cartesian. That means we're going to have our vertices at 8/5 and 0 and at 8, 0. Alright, almost done. Let's see. We found our vertices. We found our directrix. Well, we found one of our directrix. We need to get our other directrix. I know that our so let's just go ahead and look at the graph. That'll help. So what we can do is we can see that we have our vertices here. Here's my 8/5 0 and my 8 0. I will find the very center of this by just adding 8/5 and 8 and then dividing by 2, and I'll get 24/5. That's the exact center. My directrix is 8/3, so exactly on the other side of that, just take this difference, and then directly on the other side of that I'll get this other value for the other directrix. And I think that finishes that one. So let's get the other one. Alright, so let's look at this next guy. I can see I have something of this form for this next one, and specifically this guy here. I see that my E in this case, I already have it in the perfect form, so E in this case is equal to 1, and if E is equal to 1, that means I have a parabola. So I have a parabola. I know that my directrix, so let's write down that 2 equals E times D, so that's 1 times D, so my directrix must equal 2, so it is a horizontal line at y equal 2. It must be a parabola going downward because of the plus sign in the denominator. So if it were this one, it would be a parabola going up. So it's a parabola opening down. The vertex corresponds to, so let's write vertex corresponds to theta equals pi over 2, and this is going to give me the coordinates 1 pi over 2, and in Cartesian coordinates, this is for polar, and which means that that would be 0, 1 in Cartesian. So let's go ahead and see if we can graph this. And in order to figure out where this parabola crosses the x-axis, we are just going to let theta equal to 0 and then pi, and this will tell me that it crosses x at 2, 0, and 2 pi. And you can see how it corresponds on the Cartesian coordinate system. And I think we have everything for this one. In our very last example, we are just to use a graphing utility to plot the various curves. This is done for us here. E equals a 0.2. Notice the smaller eccentricity. E equals 0.4. E equals 0.6, and this is our E equal to 0.8. And notice that as the eccentricity increases, so does the oblong shape of our ellipse. And that concludes all of Calculus 2. If you have any questions, see me at the Collaborate or send me an email. Thank you for listening.